Good afternoon. Music and math, a harmonious intersection. Is there a way to effectively teach certain concepts in both music and math? There's a common core in that the elements of form, structure, logic, frequencies, creativity, they permeate both of these forms so much. And I believe strongly that we need to have lots and lots of intersection between the math and music in our teaching each and every day. And so we're going to do kind of a whirlwind tour in the next few minutes of various concepts relating to both music and math. Math and music go back a long way. In the Western tradition, their partnership traces back at least 2,500 years, when the Pythagoreans explored the math-music connection. You will note that in the quadrivium, which was the curriculum of the Pythagoreans, music was placed on the same level as arithmetic, geometry, and astronomy. However, this interpretation totally neglected the creativity of the performance of music. And in this way of thinking, music was the science of sound and harmony. In music, what makes a note a note? Usually when we think about music, we think about tones, and we think about them perhaps being at different pitches. So we might have notes that are low, or in the middle range, or high, and we will hear a note that is done here. We will hear these notes in similar families. And if I'd say, sing this pitch, I would know that we will hear it in various, what we call octave registers. Now, what's interesting about that is that music is made up of rates of an air pressure pattern. And so this is usually referred to as the frequency. And that frequency determines how high or low the corresponding pitch will be. And what's very interesting is that every time we take a note that's in the same family or an octave higher, we double that frequency. So if you have a string whose ends are fixed in place, and if you pluck the string, it will obviously produce a certain note. But now if you keep the center of the string fixed and pluck 1/2, you will automatically get a note an octave higher. Besides figuring out what makes octaves work, the Pythagoreans made similar discoveries about other pairs of musically related notes. The interval of a fifth, for instance. This is the second most important interval, octave being the most primary, the fifth being the next most important one. You will see that it's separated by what we call half steps or semitones. And this term we'll keep referring throughout the lecture. And so you'll see that this interval of the fifth has actually, in terms of semitones, 7 semitones. And we refer to the term interval simply as the distance between two notes. So the most important interval that occurs naturally is the octave, the next is the fifth, and then the fourth. And the Pythagoreans had this all figured out based on the frequency and eventually the overtone series that occurs naturally. Does the interval of the fifth, like that of an octave, result from a simple frequency relationship? Well, the answer is yes. The Pythagoreans found that multiplying a note's frequency by 3/2 raises the note by a fifth. And you will see on this next chart just intonation, and it's a tuning system that existed a long time ago. And in general, you can see that all the frequencies of the scale, and you've got the entire major scale represented here, all the frequencies of those notes can be expressed as powers of 2, 3, and 5. The frequency ratios of the just intonation scale occur naturally in the harmonic series, and they form the basis for playing certain wind instruments. So the 16 notes of the harmonic series, again, it starts with the octave, which I said was the most important, followed by the fifth, the fourth, then the third, and then it continues until you end up finally on the 16th note with several octaves higher. That's our harmonic series. Very, very important. And then by the start of the 18th century, it was beginning to be appreciated that for a keyboard to allow unlimited transposition, or being able to change keys easily, with no particular key sounding more in tune than any of the others, it was necessary to divide this octave so that each note was generated by some basic interval. We call this a scale of equal temperament. And so in the following table, you see the frequency ratios for the major scale as compared in the ancient Pythagorean tuning system, just intonation, and then finally the equal temperament. The great advantage of the equal temperament system, which is what we use today, is that there's only 12 notes. Thank God. There's still a lot of notes, but there's only 12 notes, and these allow unlimited transposition. So, and transposition means, again, that we are changing keys. Each note now, however, has several names. So F sharp is synonymous with G flat, C sharp with D flat. So if you look at this circle of fifths, you will see that this relationship of the fifth is clockwise with the C, G, D, A, E, and then counterclockwise, C, F, B flat, E flat, A flat. What's amazingly important is that this relationship of root movement of fifths forms the canon or the basis of Western music. Now, we find, again, intervals simply means the distance between two notes. But what's amazing about music and math and how this all converges, each interval name is listed here. So we start with the unison, and then we have the minor second, minor third, etc., all the way up to the octave. And you will find that there's certain qualities on each of these intervals. So you can see the abbreviation, the number of scale steps, and the number of semitones, or the number of half steps. All of those things are important for figuring it out mathematically. But the quality of the sound is critical. So if you want to harmonize very naturally, if you just start singing a melody, and one doesn't have to read music, do this, but you start harmonizing, I would dare say that you'll come out with harmonizing in thirds, very, very naturally. Or maybe sixths. They're consonant intervals. And so thirds and sixths are consonant. Now, if we want to create dissonance or things that will cause perhaps some angst or anxiety, you will not want to necessarily have thirds and sixths. You might want minor seconds or sevenths or tritones. And if you want to create kind of an ominous feel and you're writing movie music and the villain is coming, you can have double tritones. And you put that together, you get what's called a diminished seventh chord. And it feels kind of ominous, am I right? Well, that's dissonant music. Now, what music is made up of is dissonance and consonance. So you have the dissonance, but then oftentimes you will have a resolution. And when it doesn't resolve, if it stays there, we're left feeling like, well, and sometimes music has that intention, so it just depends. But the mathematical relationships inform the quality of the sound, and it all works together very, very well. Music is the pleasure the human soul experiences from counting without being aware that it is counting. So, for many people, when they think about music and math, the first thing that comes to mind is rhythm. And some people say, oh gosh, I have such trouble with rhythm. Well, music and math are so intricately combined in the way the notation is dealt with. And so, when you look at those three lines right there of music, and if I'd say to you, the numerator simply means how many beats are in each measure, the denominator means what kind of note gets the beat, and I'd ask you to read any of those lines, you'd find that they sound identical. They look different, but it's identical rhythmically. So if I'd say, here's a pulse, and that's going to be my denominator, you could pick any of those three lines, and your rhythm would come out. If this is the pulse, the rhythm would be ya-da-da, ya-da-da, ya-da-da-da-da-da. So whether it's 3/4, 3/2, 3/8, they just look different because of the type of note that's getting the beat. And then similarly, these are, well, it's just great for being able to see tractions to kids. I mean, we need to make sure that we're informing our students from early on how the math and the music relate. And so we now have compound duple, compound triple, compound quadruple meters. And all that means is that the numerator is divisible by 3. So if we have 6, 4, we're thinking 1 and 2 and 1 and 2 and. And so it's 2 beats per measure, but with a subdivided beat. So all of those things are great for teaching math and understanding how that informs the music. Next, I'd like to talk very briefly about how we vary pitches, how we vary themes in order to understand how the math and the music relate in composition. So when a composer takes a tune, you might have an example of a very simple little line. Now, one of the first ways to vary that would be to raise it, and then we may raise it again. And you can hear very clearly how that tune is the same, but it just keeps going a step higher, yes? And a very, very famous example that everybody knows, yada-da-dum, ba-dum, charge, right? You all know it. And that's simply raising that tune by transposing it up a step. Now, some of you are graduating very, very soon, and some of the students out there, when you look at lowering the pitch, this is the tune. We all know that tune. Now, starting measure 5, that same melody is lowered, right? So a nice example of being able to lower the pitch in a transposed way. We find this constantly in music. A nice example by Bach. So this is just a short excerpt from Second Fugue. So we start on C, now it's transposed to G. You have your melody on G on the top. Then you have some interlude. Now melody in the bass on C. Now on G, top. I'll stop there. So you can find C, G immediately. And so this is a common characteristic of how composition works. Other examples that we have, inversion. An inversion is when you take a melody or you take the notes and you turn them upside down. So here's an example of mirrored inversion, John Philip Sousa. So that's from the Thunderer March. Isn't that a cool example of a mirrored inversion? And then next we'll go to a retrograde. Retrograde is when you take the music and you play it backwards. So look at this example by Haydn. This is a minuet that can be done in reverse. So it starts, you have 2 lines. Then if you look at the end of the second system or the second line, and if you start looking backwards, you'll see it's identical to the 3rd and 4th line. It's just done in reverse, okay? These are some of our basic ways to vary melodies and to use mathematical concepts as we do that. Music is a secret arithmetical exercise, and the person who indulges in it does not realize he is manipulating numbers. So now I'd like to talk a little about, we're going to fast forward to the 20th century, and it's possible to explore pitch names with integers. And so a method of composition that was developed in the 20th century by Arnold Schoenberg, dodecaphonic composition, 12-tone music. I would like to show you how you can have pieces with all of the pitches written out in your 12-tone matrix. You can also equate that with integers, and it is very, very cool how it all works. And so in integer notation, we assign a number to each pitch. Now, I want to make sure that you're seeing when you get to the 7th, the minor 7th, which is 10, we use a T, major 7th, 11, a small E, octave, and O. But you can see that we can have a whole set of pitches here, and they're notes, but they're just simply using integers to describe them. And then you can transpose, you can invert, you can retrograde, invert. So all aspects of the are possible. I would like now to show you in some music how this works. So here's a matrix analysis of Rosalie Finney's Variations on a Theme by Baird, which I'm going to play for you in a moment. And you'll see that we call the P0, the prime or the original. And so he wrote this work based on a tune by Berg. Berg was a disciple of Schoenberg, and they all were devoted to a certain type of composition that explored different ways of composing. So the tune, G, B flat, D, F sharp, I'm reading across the top, G, B flat, D, F sharp, A, C, E, G sharp, E, C sharp, E flat, F, that's the prime. That can now be transposed, and then you'll see how each note it transposes. You can come down and do them inverted. You can come to the left and do them backwards or retrograde, and you can read from the bottom up and you'll get the retrograde inversion. So it's very, very cool, and it all works beautifully. And I'd like to show you how this particular work, the way the notes are constructed, you'll find that there's also triadic, or meaning chords occur kind of naturally, minor, augmented, major. So sometimes it sounds tonal, even though it's written in an atonal method. So when this work begins, you have P0, that's the prime, the original, and you see how the notes come out chordally. So it's first presented vertically. And now it's going to be linear. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's your 12-tone row. And then some chords that surround that, etc. And then when you go to the very end, you'll find that the composer takes that row or set once again, but now it's transposed to P11. And here again, the row is presented linearly with all the 12 pitches. And finally, back home, P0, and it ends like it began. All right. I'd like to take a moment to play just an excerpt from this work due to time. But what I'd like you to think about as you listen is simply how, number one, how wonderful music is and how blessed we are to have this art form. How wonderful math is in the way that these two forms work together to inform each other. The way the math helps the music to really make sense. The way these two elements work in tandem. So an excerpt of Rosalie Finney's Variations on a Theme by Berg. I hope that this brief lecture and performance have given you a taste of how music and math are so crucially tied together. There are certain mathematical structures inherent in all works of music, but these structures are not necessarily presented in the form of equations. The language of math is a powerful and wonderful tool for comprehending and communicating this underlying structure in music. It is crucial that we have the music and math correlations as part of our curriculum in ways to be able to transmit this to our students. To move from STEM to STEAM, we must all be effective advocates for arts in today's STEM-concentrated funding and research. Musicians need to be able to succinctly articulate and represent how math and music really do work together and the positive effects on the cognitive and creative processes for all of our students. Mathematics and music, the most sharply contrasted fields of scientific activity which can be found, and yet related, supporting each other as if to show forth the secret connection which ties together all the activities of the mind, and which leads us to surmise that the manifestations of the artist's genius are but the unconscious expressions of a mysteriously acting rationality. Thank you so much.